KW, this is 10 to the minus 7, 10 to the minus 7. You write ALOH 3. OH minus, so far so good. And then you do I, because that's what we didn't do before. This you don't care about because it doesn't appear in the equilibrium expression. It's a solubility product. I keep emphasizing that. This one is 0. That's what we wrote here. We didn't write it there, but that's what we assumed when we just shift the change column. But this is 10 to the minus 7. Right there. Go ahead, ask your question.
You one that has like a set, like, we know with the hydro, everyone's like the ones where they give us like the amount of saturated one. So I'm, like, I don't know how to solve like that initial number at 10 to the -7. Like, I mean, that one's given, but like in the problem.
But I'm not done with the problem yet.
Okay.
Let me finish this problem. No, if you don't like that problem, there's hundreds of them out there. Possibly thousands.
How come you don't do an ice chart for water?
Because if we just have pure water, remember I did this before. And I did do the ice chart for you before. I said, where do I have it here? Well, I guess I didn't. I did it a couple days ago when I set up the pH scale, remember that?
Yeah.
But I said you had QH2O gives you H3O plus. I have it here, but I don't want to mess that up. Minus, and I said 0, 0, plus X, right? That's the ICE. And I didn't do E because 0 plus X is X.
Yeah.
Then I said KW X squared. And that's where I got 10 to the minus 7.
Okay.
And so, anytime, and remember I talked about this when we did our weak acid dissociation already. I didn't put one of those in this. Okay, I didn't forget about it. Did I have it on the last quiz? No, I guess I didn't. No, I made this quiz too easy. No wonder everybody got 26 and 27. Okay, we'll go back to this. I have 24s and 25s, whatever those numbers were. They're just numbers, right? Okay, so anyhow, I did that. That's how and so whenever I have water, if all I have is water, this is what I know I start with. Then if I put something else in, things start changing. So I just said, let's start with that for the hydroxide. Then I said my C, that stays the same as before, minus X, X, 3X. And then I go to solve the problem, because somebody said it doesn't look like a common ion problem, but there's my common ion again. I keep circling common ions like that. That's one way to remind yourself about that. So now I have and you say, darn, I can't solve that. And that's what you said. And then you say, oh, but I know all about approximations. This is really small, so this X must be pretty small. So I'm going to make an approximation. Somebody asked me about that the other day. In other words, whenever you're making an approximation, it's because one number is much smaller than another number when you're adding and subtracting, and so effectively it doesn't change it. If this were a really big number, you'd have to say X must be a really big number, then this must be small compared to this, and then again simplifies the problem so you can make an approximate estimate of your solution. You're going to have X, you're going to ignore this, and notice when I do this sort of thing with it, that just means I'm ignoring it, I'm not canceling it out or anything else. So I have, and it's really easy to solve now. You can do that in your head, right? I'm not going to dive. I'm going to try it anyhow. If not, I'll pull out my calculator. X is minus 12. Notice the biggest change here. Here aluminum is 10 to the minus. Wait. Did I do it wrong? Well, let me get my calculator and see. First of all, 10 to the minus 7th cubed is,
Is it not time?
no, it's 10 to the minus 21. I cubed it.
Wait.
This is 10 to the minus 7th cubed. 10 to the minus 7 times 10 to the minus 7 times 10 to the minus 7th is
Negative 21, right?
10 to the negative 21, right?
So,
And then I divided into this, and I got 1.30. I subtracted exponents in my head. I can still handle small numbers, but you can divide it on your calculator if you want. It better come out the same. Did it? Somebody said that. They weren't even giving me a chance. You always want to make sure when I say these things that they're right, because sometimes they're not. Okay. And then you don't want to come up to me later because I said I couldn't have made that dumb mistake or whatever I would say. The important thing here, okay, it's right. You got it? No? Darn calculator's failing. Just gotta fail the exam. Okay, good. So here, notice, this is the thing I talked about the last time. Here what we could have expected, it's 2.63 times 10 to the minus 9th doing this calculation, but it is actually much smaller because of the common ion effect. The extra hydroxide that I had from the water pushed this dissociation back in this direction. So we didn't get quite as much dissociation as we would have expected. So that's the so-called common ion effect. And now, when we do the hydroxide, it's going to be 10 to the minus 7. What I wrote right here somewhere, plus 3.90 times 10 to the minus 12. First thing I'd say, boy, my approximation was okay. I could ignore that, right? Because it would be adding those two together, 1.000039 10 to the minus 7. So when I added, that's what I got. And I said, I'm happy with 3 significant figures. 3 significant figures. But the point I was trying to make is my approximation is okay. I was justified in making that approximation. Yes?
Can you do another one that's not involved in?
Well, I just wanted to do one more thing here. Then I'll pick something else. I'll find something. I think I see one right here.